Although the title of our presentation says Compute Substrate for Software 2.0, what it's really about is the age-old story of the hare and the tortoise, in which the sporting rabbit lets the tortoise run ahead for a couple of decades in order to catch up with it very quickly in about a year when he decides to. This, in a nutshell, is a summary of our situation with machine learning compute demand and Moore's law, which has been governing the ability of the semiconductor and the hardware world to provide compute capacity to machine learning. So the two key curves to focus on here are the orange one and the blue one at the bottom. And what you can see is that there's this very rapidly growing gap between the two. I tried to overlay a couple more just for thought experiment purposes. So let's say optical or analog and nanowires works out, we get a one-time speed boost of about 1000x. That's what's shown on that purple line. The two dashed lines are showing Moore's law as it pertains to clusters. So in one case multiplied by 10,000, so this is kind of reasonable cluster sizes today. In another case, it's multiplied by 100,000, which is larger clusters, which we're trying to enable and probably others are going to bring forth in the coming years. Either way, you can see that the compute demand for machine learning is skyrocketing. It's just a matter of time when the two curves intersect. And in other words, when the rabbit catches up with the tortoise. So the two ways that we've chosen to try to work on this problem is, for one, enabling huge scale-outs, so bigger ones that have been attempted before, so enabling machines that put us into the 100,000 node territory. For the other is dynamic execution, and the idea here is that we would like to embrace every way of intelligently dropping work and foregoing computation and machine learning, akin to what our brains do, in order to take the current slope of the machine learning compute demand curve and bring it down to something much more compatible with Moore's law. So a couple of slides about scale-out. So large clusters are already normal. Pretty much all modern models are being trained on them. Some of the biggest ones are even being inferenced on them. At this point, we had to transition from a shared memory programming paradigm to a private memory programming paradigm, as every node in these clusters has a private memory space. Usually they have a bunch of GPUs. Data movement between the nodes needs to be explicitly controlled and planned. For a while, this was made a bit simpler by embracing the data parallel view of training for models. That era is kind of over. Models are too big to fit on a single node now, so model parallelism is the norm that's being deployed today, and with it, one is exposed to the full complexity of cluster-level programming. So hardware and software-wise, we wanted to enable the largest clusters ever. And from the hardware side of things, what this meant was tightly integrating networking and compute on a chip, enabling computation to be scheduled directly at the level of packets, exposing packet routing control to our graph compiler. All of these together are aiming to let us build clusters with hundreds of thousands of nodes in them and expose all of this huge machinery as a single device in PyTorch so that machine learning practitioners don't need to worry about parallelization, communication, all these items that are below their preferred level of abstraction. They can focus on developing their models. From the software side, what this means is a move from shared memory programming paradigms in which each processing unit can see the entire memory space, and when one needs an array element or a tensor element, they can just issue a load and get it. When one core sees a tensor manipulation, say a transpose or an unsqueeze, a lot of these just come down to different offsets and striding in the same memory buffers that are visible to all of them, where the primary compiler challenges were creating a parallelized schedule of the workload and then loop nest optimization. We move into a world in which chunks of data are owned by particular nodes. There's only local visibility of data. Any communication needs to be planned and implemented explicitly. Tensor manipulations, so like that same transpose, become not only manipulations, so not only local transposes, but in the general case, also required scheduling of data movement between nodes to implement, as shown in the diagram here. In this kind of world, the hardest challenges are with data transfer, communication, consuming tensor manipulations without having to stall the machines and stop doing math. We try to solve these problems holistically by retrofitting our hardware with a variety of features that try to help, and then splitting them effectively between our runtime software layer and our compiler. A little bit about dynamic execution. So what all is dynamic execution? It's enabling control flow at runtime so that a machine learning model practitioner can say, well, if the power in this tensor is above a certain threshold, compute the remainder of the neural net this way. If it's below, compute it another way. This is actually currently missing, and it enables the level of control to machine learning practitioners that should, by a good degree of slope reduction to that machine learning compute demand curve. Fully embracing sparse compute, and in particular, I'm referring to dynamic sparsity here, so sparsity in activations, sparsity in weights during training. Fully embracing dynamic precision, so that at model control or at heuristic control, we can choose fine-grained what data type to use for what computations. And finally, taking compression for all it's worth. Machine learning presents a lot of compressible data. This needs to be embraced fully and used as far as it can be. To give the next level of idea of what this means, I make an example of a matrix multiplication that can be done in order n complexity. So beginning with the left, we start with a standard matrix multiplication, which most of us here know is, when implemented naively, it's an n-cubed operation. We move to the middle, where we assume that the model has intelligence within it to determine which blocks of the output matrix need to be computed for a given example, and which don't. If the hardware and underlying software stack support making use of this, it enables a linear speedup. So you hit 50% sparsity, you speed up 2x theoretically. You hit 90%, you speed up 10x. So this is pretty nice, but it's far from starting to close the gap. However, the rightmost example actually makes a fairly serious dent in the problem. Here we show an example where chained operations produce sparse results. So one of the operands is sparse, the result is also sparse. If the underlying hardware and software support it, this offers theoretically 4x speed boost even with just 50% sparsity. With 90% sparsity, we cross the 100x mark. The important thing to notice here is that regardless of the numbers shown here, the real significant factor is that this meaningfully reduces the slope of the machine learning demand curve and brings it into something like compatibility with Moore's law. A little more on this topic. It's generally applicable, works for training and inference. It also works for models that aspire to generality, like GPT-3, so models that try to do a lot of things without a specialization. Pruning, which is currently somewhat popular, fails at both and only works for models that are relatively specialized. It certainly doesn't work for training. Now, as I mentioned before, this approach requires models that can dynamically choose subsets of blocks to compute during each pass. There's a number of ways that machine learning folks have figured out to attack this problem with. Mixture experts from Google, locality-sensitive hashing-based approaches to determining the important outputs, pre-pass-based approaches where you do a simplified pre-pass and use that as a map of what to compute. More close to our territory, this requires hardware that can really fully utilize this kind of model structure and deliver that speed up that I was advertising on the previous slide. So we strive to make our hardware such. And with that, I hand it off to my colleague Jasmina, who's going to give you a lot of details about both our hardware and software architecture and how we implemented the details of it to attack both scale-out and dynamic computation.
Thanks for the introduction, Ljubisa. I will take you guys for a deep dive through our architecture and software, and I'll describe them interchangeably in order to give you a good sense of our holistic solution. Here we go. So I'll start off with a high-level view of Grayskull. Grayskull is the name of our first production chip, and it's also the first incarnation of the architecture that I'll present today. It's a cluster on a chip, so it's composed of 120 compute cores. Now, each core has its own unique instruction queue, and it progresses independently at its own pace, while occasionally communicating with the other cores in the grid. The cores are connected via a 2D bidirectional torus NOC. The NOC was architected in-house and it's highly optimized for machine learning workloads. In terms of connectivity, the PCIe block connects to host, and DRAM is also accessible from every core of the device. Now, zooming into a single core view, as Ljubisa mentioned, everything that happens on our system happens in the format of packets. Packets get computed and packets get moved around the NOC and the memories. The packet processor is a 3 teraop vector SIMD engine. It's powerful but very, very flexible and programmable. It can actually execute C code based kernels, and we've mapped a large number of PyTorch math layers onto it. It contains DSPs with a multitude of various data formats, but most importantly, it actually natively handles sparse compute to achieve speedup. Next, the packet manager, it's in charge of executing all data transfers between compute, memory, and between the cores as well. And it completely deburdens the compute engine from all of the data movement complexity. Each core also contains 1 megabyte of local SRAM, and as mentioned, has access to DRAM as well. Finally, there are 5 RISC processors on every core, small but powerful single-issue processors. They execute our runtime software. So, continuing on with the challenges that Ljubisa introduced earlier, we need to parallelize every compute layer across the cores of the device. So to do that, we split the tensors amongst the SRAM blocks on each core. And we also need to move the tensors between the cores during runtime. So sometimes we're moving the tensors between the different compute layers, but sometimes the tensors need to be moved around during the compute itself. In addition, the application graph that we get from a machine learning framework, it doesn't just contain compute instructions. Most often, there are various kinds of tensor manipulation instructions between the compute as well. And these TMs, they don't change any of the values inside the tensor, but they reshuffle the data within the tensor. So to actually correctly connect the compute nodes, all of the data reshuffling has to happen during runtime. And all of this has to be executed while achieving high performance, meaning we have to overlap compute and data transfers. We have to efficiently use the NOC. We have to efficiently use the memory bandwidth when we read and write the memory. So combining all the goals together leads to a compound complexity, which we attack with our full stack approach and a tightly coupled software-hardware co-design. So three main architectural components are here. First, the AOT graph compiler, which parallelizes compute and packetizes all the tensors. Next, in hardware, the movement of packets is facilitated by the packet manager block. And finally, in runtime software, the runtime software works together tightly with the packet manager to dynamically allocate memory space in SRAM on every core, but in off-chip memory as well. And I'm going to describe these three architectural components next. So first, the graph compiler. It takes each tensor, it splits it into multiple mini tensors, and for each mini tensor, it generates header information, which essentially then just becomes a packet. Now, each packet is assigned a packet ID, which is stored in the header, and everything that happens further during compilation as well as during runtime is done in terms of these packets and their IDs. So there are no pointers and there's no pointer manipulation. Now, there are many different ways to packetize a single tensor, and some packetization strategies are more desired than others. First, to utilize the NOC bandwidth well, the compiler has to choose the right packet size, and packets can be heterogeneous in size even for a single tensor. And second, we have to execute all the TM instructions during runtime. So technically, the TMs can be executed via complicated read-write memory patterns. It's easy to create the patterns themselves, but this can easily kill performance during runtime. So what the compiler does is it performs an optimization where it assigns some TMs to be performed in line midstream by the packet manager, while other TMs are expressed as memory access patterns. So it actually generates a combination of these two approaches in order to maintain performance. Next, the packet manager. So to understand, the easiest way to understand what the packet manager does is by looking at what packet compute does. So the packet compute engine is powerful, very programmable, but it has only a very local view of what is happening in the system. It simply gets input packets to be computed from the packet manager, and once it computes them, it sends output packets back to the packet manager, and that's it. It's actually the packet manager that has a global view of what is happening across the entire chip. So it has access to NOC, it has access to local SRAM and to remote DRAM, and it also has insight into what is happening on all the other cores in the system. So it's able to perform all the required multi-core synchronization, all the required data movement, data storage, and TMs as well. And the way that it does that is via the three building blocks that it contains. So at the very, very bottom, the router moves packets across the NOC, and in some ways it's a textbook router. So it takes care of back pressure, it guarantees ordering, it guarantees deadlock-free execution, but it's also highly optimized for machine learning workloads, and it has a very flexible and very efficient multicast and gather operations. In the middle, the data transfer engine, it's tightly coupled with the router, but it operates on a slightly higher level of abstraction. It's actually aware of the application that it's executing, so it receives an entire instruction queue from the compiler, and the instruction queue tells the data transfer engine how and when to take care of all the required multi-core synchronization and handshaking. Like data ready signals, memory space ready signals, and so on. It's actually aware of the state the other cores are in, and it uses this information to, for example, decide when to start sending data to remote cores or when to allocate space in its local SRAM in order to receive data from remote cores. So finally, the tensor manipulation engine at the very top, it contributes to performance in two ways. So first, it performs the complex memory access patterns assigned by the compiler, but second, it has a tiny bit of storage within it. So within this storage, it can actually load a single packet and reshuffle it in place. And this way, the compiler can program the TM engine to perform tons of tensor manipulations efficiently inline midstream as it's reading or writing to the memory. So finally, the runtime software. So the packet manager works in tight collaboration with the runtime software, primarily in order to achieve dynamic memory allocation. So all buffers are allocated and deallocated during runtime, and the runtime can actually control the storage target as well. So this allows us to store buffers in SRAM if they can fit, but also gives us the flexibility to overflow to DRAM or even to host memory space if necessary. And second, the runtime software enables control flow and control flow graphs to run on our hardware. So the RISC cores can actually execute any type of conditional instruction within the graph, so if statements, for loops, while loops, and the resulting control flow decisions are reflected by jumping around in the instruction queues that both packet compute and packet manager are executing. So finally, a brief look at our flexible scheduling and parallelization. So obviously there is a desire to support very flexible parallelization, and the reason for that is because any single parallelization approach eventually plateaus as you increase the number of cores across which you parallelize. And the way to maximize performance is to stack up as many parallelization approaches as possible. So on our architecture, models can be pipelined, and actually each pipeline stage can execute multiple compute layers in sequence before progressing to the next pipeline stage. In terms of model parallelism, we can do the simple case where each layer is parallelized across the entire chip if that's possible, but also layers can execute across any number of cores of the chip and run in parallel if the graph contains parallel opportunities. So tying it all together, our full stack approach has unlocked a number of desired targets. First, we achieve high performance by enabling a tremendous amount of concurrency. So not only does every core progress independently at its own pace, but the building blocks within the core, so the packet manager and the packet compute, they operate in parallel too. And as a result, compute and data transfers are fully overlapped. Second, on a system with tons of asynchronous concurrent behavior like this one, the ahead of time graph compiler has no chance at accurately predicting buffer lifetimes or managing memory well. So we leave this task to the runtime software. Now, the compiler generates storage related hints, but the actual memory addresses of each buffer are determined at runtime. And third, most importantly, we have fully unlocked dynamic execution. So we've enabled runtime compression, and we achieve speed up from the increased amount of data locality that compression brings. And again, the runtime dynamic memory management ensures that. The packet compute engine can natively handle sparsity, through which we achieve speed up as well. And finally, the RISC cores can execute performance penalty-free control flow on the device right at the edge of the compute. So that's all for me. This concludes our deep dive, and back to you, Ljubisa.
Thank you, Jasmina. Jasmina and I have spent some time talking about high-level architecture, about the macro-level situation facing machine learning and computer architects. I'd like to conclude this presentation by talking a little bit about TensorStorm as a company, about our products, about our status, and plans for the future. TensorStorm was founded 4 years ago to develop a ground-up computer architecture for the new age of data-centric computing. Since then, we have grown from the 3 founders to around 70 employees across Toronto and Austin. Our team has deep expertise in CPU, GPU, and FPGA-based approaches to parallel computing. Over those 4 years, we have worked on 3 chips: Drawbridge, which was a small 14nm test chip; Grayskull, the part that Jasmina talked about, which is currently in evaluation with multiple large customers. Grayskull will be transitioning to production in late fall this year. And Wormhole, the first part that fully realizes our vision of converged networking and compute. Wormhole includes an integrated network switch, 16 ports of 100 gig Ethernet, 6 channels of GDDR6, and a compute fabric similar to Grayskull. We expect to have Wormhole in-house by the end of the year. It forms the basis of our plans to enable larger compute clusters than anyone has been able to build before. This slide shows the progression of BERT performance numbers with various aspects of dynamic execution enabled. The first number, which leads the industry on performance per watt, is with no conditional execution enabled and 16-bit floating point numbers for apples-to-apples comparison to GPUs. The second assumes a very light subset of conditional execution enabled. And finally, the last assumes modifying BERT to include sparse operations as described earlier. It's still a work in progress number, here to show the promise of our approach primarily. We've spent an equal amount of time on our software stack over the years. We architected our software to aim for full compiler generality from the get-go. The list of machine learning models below shows a subset of workloads that we're using to test our compiler generality. You can see representatives from all major neural net categories in the list. Our software is under evaluation by customers currently, and we will open up the beta version of it for public access in our development cloud on November 1st this year. While we spent a lot of time on functionality of software, we also had strong goals in the areas of usability. In order to make our product maximally approachable to the ML community, we implemented complete integration with PyTorch. Through TorchScript, PyTorch's preferred deployment flow, Onyx, as well as a native device. Regardless of how many processors are used in an instance, a machine learning practitioner sees them all appear as a single device in PyTorch, avoiding the need for them to worry about parallelization, communication, all these difficult aspects of cluster-level programming. Finally, we will be shipping an automated deployment flow, allow existing models that have been trained on GPUs to automatically gain benefits from our conditional compute features and approach. So in summary, We're going to slow the hare down, speed the tortoise up via conditionals and scale. And we're going to do it in a way that is maximally easy to adopt and use by the machine learning community. I hope you all enjoyed our presentation, and thank you very much for listening.